All right, we've talked about critical points, so we know how to find them. We've talked about local extrema, and we found them graphically. We'll find them analytically in the next section. Now we talked about absolute extrema, and now we're talking about how to find them. All right, this is going to conclude this section, and we're going to start with another theorem. Yes, calculus is really one of those points that just gets a lot more theoretical, and it doesn't stop in Calc 1. So, theorem. If f is continuous on an interval a to b, don't worry, this is different than the last one, even though it's starting out the same. The absolute extrema, plural, must either be at critical points in AB or the endpoints of that interval. So again, the theorem in the last section said that if f is continuous on an interval, then we're guaranteed absolute extrema. Well, this is just going one step further and saying those guaranteed extrema either have to be at critical points in that interval or at the endpoints, just like we saw over here. All of these, well, not all of these are good examples because literally only one of these is a continuous function on a closed interval. Everything else is either on an open interval or not continuous. But you can see that it will either be in the middle at a critical point or at the ends. And then there's something else to watch out for that I'll make as a note, but not an official theorem, because the book doesn't present it this way, which is a little odd. If f is continuous on an open interval, well then, and it's kind of hard to decide how to phrase this, we have the same thing. If f is continuous on, actually we can say any open interval. If f is continuous on an open interval, we still have the same thing, but the absolute max and absolute min might not exist. You kind of have to look at the endpoints and check. Oh, all right. So if f is continuous on an open interval, then if extrema exist, they're at critical points. If absolute extrema exist, they're at critical points. But you need to check the endpoints to determine existence. We're going to use this in the homework. I definitely am planning on doing a problem where we use this. So don't worry too much if this red part doesn't make too much sense. It's less important, and we'll go over it later. The white part is really important. So for finding absolute extrema, that's what we're doing in this section. How did we get back here? Oh, oops. This red part is supposed to be on the next page. We're finding absolute extrema. So if we're on a closed interval, they definitely exist. Look at the endpoints, look at the critical points. If it's an open interval, they may or may not exist. We still have to look at the endpoints, or like the limits, technically, the limits and the critical points. I'll talk about that in the next video, that selected homework problems video. Let's do example 4. Find and classify absolute extrema. So if it's a closed interval, you just find the biggest and the smallest. Find all of our candidates and then pick the winner. Part A, going to be f of x equals, I'll add a part C to make this a little bit more clear. Negative x squared plus 3x minus 2 on the interval 1 to 3. So absolute extrema on a closed interval, continuous function. Right? This is continuous. The interval is closed. So the extrema must be at the critical points or the endpoints. So find the critical points and find the endpoints and pick the biggest one and the smallest one. And pick the biggest function value. That's all you have to do here. So we go, all right, let's start with the endpoints. All right, so step one, going to be looking at the endpoints. So the endpoints are when x is 1 and x is 3. These are going to be our candidates. Candidates are going to be in green. So 1 comma something and 3 comma something. What are the function values? Plug it into the function. Again, we can use a graphing utility like Desmos. Our function is f of x equals negative x squared plus 3x minus 2. Now we're looking at the endpoints. F of 1 is equal to 0, and f of 3 is equal to negative 2. So these are our first two candidates for absolute extrema, because we know it's a closed interval. We know it's a continuous function. We know there has to be absolute extrema. So we just find all the candidates and then pick the ones that are the biggest and the smallest y values. Let's find critical points. Well, when is the derivative equal to 0? When is the derivative undefined? We found out how to find critical points in that first one. Let's make sure they're in our interval as well. So when is this equal to 0? That's going to be when x is equal to 3/2. We've got another candidate, everyone. 3/2 is 1.5. So make sure to specify, yes, that's in the interval. We got two more candidates. 3/2 or 1.5. What happens if you plug that in? You get 0.25 or a quarter. Decimals are usually easier for absolute extrema because it's easier to compare which decimal is bigger as opposed to fractions, right? Like decimals is much quicker to compare it compared to this. Yeah. These are actually kind of close, but 8/3 is bigger. But decimals are quicker, so decimals can be a better solution here, but both are fine. So that's our other candidate. We also have to find out when does f prime not exist. When does this not exist? Well, this is a line. It never doesn't exist. It always exists. So there's no candidates for that part. Endpoints, critical points when the derivative equals 0, critical points when the derivative doesn't exist. So these are our three candidates. All we have to do is align these candidates on the wall and say, you're the tallest, you're the shortest, or you're the tallest in the negative direction. Don't tell that to somebody. Anyway, so line up the candidates. Look at our y values. Our y values are 0, -2, and 0.25. What's the biggest? This is the biggest. What's the smallest? Oh, I forgot to erase. Oh, well. This is the smallest. So we're going to say, and the wording here is important. We're going to say that the absolute max, the absolute maximum of this function is 0.25, and it occurs when x is 1.5. The absolute minimum is -2, and that occurs when x equals 3. The phrasing is important. When we say absolute minimum, absolute maximum, we're talking about the y values. Now, a lot of times we care about where that happens. We care about where the x is. It's really weird when it looks like I'm talking underneath. Even though technically I think I'm on top. Technically, I'm actually on top. I'm just halfway see-through, but it looks like I'm underneath. Looks like I'm between the chalk and the chalkboard. Anyway, so this wording is important. Absolute max is always a y value. Always the y value. Okay. And again, we could see this graphically. If we're just looking at the interval from 1 to 3, that looks like this. Well, what's the biggest? The biggest is right here. The smallest occurs right here. Biggest value is 0.25, smallest value is -2. And then it occurs exactly where we said it would. All right. Let's do one more problem and then we'll adjust the final problem. Give you guys a bonus problem. F of x equals x squared minus 3x to the 2/3 on the interval 0 to 2. Now, I haven't done this for a while, but it is good practice every once in a while. I recommend pausing the video right now and try to do this problem on your own and see if we get the same answer. All right, hopefully you did so. Again, we are going to look at the endpoints. Those are going to be some of our candidates. Well, again, draw the candidates in green. That's going to be when x is 0 and when x is equal to 2. We'll plug those into a calculator, or you could do it by hand. You could do all of this by hand, but you don't have to. X squared minus 3x to the 2/3. If you do it by hand, remember 3, that's the cubed root, the denominator. 2, that's the exponent, and it only applies to the x. It does not apply to the 3. So f of 0 is equal to 0. And f of 2, I would actually do these by hand. Oh, this is kind of messy. Is about -0.762. I would do these by hand. It would just take up a lot more time, and I'd rather spend my time on other things. Algebra review is important though, so let me know if you have questions about that. So those are some of our candidates. Then other candidates are critical points, specifically when the derivative equals 0 and when the derivative doesn't exist. So let's find these other candidates. F prime of x, we'll use the power rule to get 2x. Minus 3, bring the exponent down and subtract 1 from the exponent. 2/3 minus 1, that's 2/3 minus 3/3, -1/3. And we could simplify a little bit to get that this derivative equals 2x minus 2 over the cubed root of x. And again, remember that negative exponent just means it's in the denominator. And the rational exponent, this says that it's x to the first power, and this says it's the cubed root of x. We're curious, when is this derivative equal to 0? This one, this one's a bit more tricky. We're going to start by multiplying both sides of the equation to get rid of the denominator. So multiply both sides of this equation by the cubed root of x. And when we do that, the left-hand side is very nice. The right-hand side does need to distribute. That's going to give us x to the 4/3, x to the 1/3 times x to the 1. Add those exponents, 4/3. So they at least cancel on the other one. And we can continue working with this. Add 2 to both sides. You're going to get 2 equals 2x to the 4/3. Divide both sides by 2. And then raise both sides to the 3/4 power. 1 to any exponent is still 1. On the right, we multiply those exponents. And that just gives us x to the first power. We have another candidate when x is equal to 1. Another candidate in green. What's the function value here? -2. All right, so we have 3 candidates. We also have to look at when does this derivative not exist. So let's look at this derivative. F prime of x equals 2x minus 2 over the cubed root of x. Where does this derivative not exist? And you might say, oh, we can't take the square root of a negative number. And that's true. Square root of a negative number is imaginary. But this is not a square root. This is a cubed root. And odd indices, 3 cubed root, 5th root, 7th root, odd indices are perfectly fine to take roots of. But we also don't want to divide by 0. This is undefined. When we divide by 0, that's when x is equal to 0. So we have our 3rd candidate, our 4th candidate. Oh no, you're trying to pull a fast one on me. The 4th candidate's the same as the 1st candidate. You can't run for president. Never mind. We already have that candidate. This is a duplicate candidate. All right. We're already taking care of that. So again, 3 candidates. We pick the smallest, we pick the biggest. And here they're on different pages. It can be helpful to write them next to each other. Also 0, 0, and 2, negative 0.762. All right, so pick the biggest, pick the smallest. And always look at the y value. And that gives us our answer. So we have an absolute max. Absolute maximum is what is the biggest function value we have? The biggest function value we have on this interval is 0 when x is equal to 0. And we know the absolute minimum, the smallest this function ever gets, is negative 2, and that occurs when x is equal to 1. We should be able to check our answer with a picture. Let's specify that this domain is only going from 0 to 2. Well, this is the biggest. 0, 0. Is that what we said? Great. Here's where we're the smallest. 1, 2, negative 2. That's what we said. That's great. And again, if we weren't looking at everything, then this would only be a local extremum, not an absolute extremum. But this is a critical point because the derivative doesn't exist. We have a vertical tangent line. All right. But again, this is actually what we're looking at. So part C, I just want to slightly change things a little bit in part C. Let's look at the same function. The same function, but now let's look on the interval. What if it's open? Well, if it's open, it's a slightly different graph. And the method is a little different. If it's closed, we're guaranteed absolute extrema. We had that back here. If it's closed and continuous, we're guaranteed absolute extrema. But if it's open, we're not guaranteed absolute extrema. We have to look at the critical point still. And then also look at the end behavior in that interval. Look at the limits at either side. So we're going to look at the limit as x approaches 0 from the right. Because we have to look at we have to basically look here from our interval. So if we're approaching 0 in this interval, we have to be approaching 0 from the right of this function. And I don't think you'll see this very much in this section, but I did want to make a point about it. And that's going to be 0. This function's continuous. Remember that if a function's continuous, the limit is the same as the function value. That's the definition of continuity. Y'all thought you were done with limits. Well, you thought wrong. So because it's continuous, the limit is just the function value. We can use direct substitution. We can just plug it in. And similarly, the limit as x goes to 0, the other endpoint is 2. We're going to approach 2 from the left because we want to approach it from the inside of the interval. Again, using direct substitution, we're going to get negative 0.762. And then our only actual candidate is that critical point, which is the same critical point as before, which was 1, negative 2. We also had a critical point at 0, 0, but 0, 0 is not in our interval here. Right, 0, 0 is not in our interval, so that critical point doesn't get included. So now for our absolute max and absolute min, it's almost the same. But now when we pick the biggest and we pick the smallest, so this is still the smallest out of these three things. I really should have written these in green. Right, we still look at the biggest and the smallest. The difference is that here, since this is a limit, then that means that there's no absolute maximum. Okay. So if the biggest, if the max or the min is at the endpoint or limit of an open interval, then there's no max or min. So if we slightly change this problem, then the answer becomes that there's an absolute minimum of -2 at x equals +1, just like before. But now there's no absolute maximum. And the reason why there's no absolute maximum is because the absolute maximum would occur right here. We get really close to 0. 0 would be the biggest, but because the interval's open, we get really close to 0, but we can never hit it. We can always get closer to 0. So what we've done is we've changed this problem from this being our situation to this. Let me just edit these points to look correctly. These should be blue open circles. So now that they're open circles, there is no absolute maximum. Because you'd think if there were an absolute maximum, and this is what we calculated by looking at the limit from the right, that's why we did the limit from the right, because on this domain, the limit from the left makes no sense. The function is not defined here on the left, or at least that's not the interval that we're looking for. So it would be here if there were a maximum, because there's an open circle. Any point that we choose on this graph, there's a point that's bigger. There still is an absolute minimum because that hasn't changed. So watch out for that a little bit. It doesn't pop up in the homework too much, but I did want to talk a little bit about it as well. We'll do more in the next video with selected homework problems. Enjoy, good luck, and just like this, hold on. We're done with the math, but I got one more thing for you guys going forward. Let's change our domain a little bit. One little special treat. You don't have to stay for this. One little special treat right here for all of you guys. Okay? And the special treat is a smiley face to bring you on your day. Have a great day, and don't make fun of how weird this smiley face looks like. Bye-bye.